Okay, so we can see your screen. Okay, so let's start the session. So this is the session on graph algorithms. Uh, and we are going to keep the talk as usual to 8 minutes each. And unless there are clarifying questions, let's just keep it for the end of the session, at which point we can ask questions to the speakers as well as have a panel discussion. Okay, so to get us started, the first speaker is Uri Meir, who is going to tell us about graphs, comparison graphs as a unified method for uniformity testing.
Okay, so can you hear me all right?
Yes. So,
okay.
And I'll give you a warning about a minute before the end of your talk. Before 8 minutes, I'll give you a warning at 7 minutes.
Okay, good. So hi everyone, my name is Uri. I'm a graduate student at the university and I'm going to talk about comparison graphs. So let me give you some background. The problem we consider is uniformity testing, a problem in property testing. And the test subject is a distribution D over a domain size N. And the inputs we're going to get is Q independent samples from the distribution D. And our task is to distinguish between two cases. One is that we have the uniform distribution over the entire domain, and the other is that we have distribution that is epsilon far, say in L1 distance, from the uniform distribution. Okay, so our parameters are the domain size N and the proximity parameter epsilon. And the problem was already solved like 10 years ago. We know that square root of N over epsilon squared is the right sample complexity for that. It's the amount of samples that are necessary and sufficient to solve that. Okay, so this is a brief history. The problem was first considered by Rubenfeld, Smith, and White in Fox 2000, and implicitly by Goldach and Ron a bit earlier. And the idea is counting collisions. And the result they show is that the sample complexity is between square root of N and square root of N over epsilon to the fourth. So the dependency on N was quite clear, but the dependency on epsilon remained a mystery for quite some time. And roughly 10 years later, it was solved by Paninsky, and it showed that the dependency on epsilon is 1 over epsilon squared. And it had a small caveat that was fixed by Chen, Nicholas, Valiant, and Valiant a bit after. And another paper that I want to mention is a paper by Nicholas, Gulikis, Peebles, and Price from 2016 that actually showed that the original idea of counting collisions can be made optimal. So with optimal analysis, it can actually succeed with square root of N over epsilon squared samples. Okay, so what is the idea of the original tester? And this is by Goldach and Ron. So we have this magnitude called the collision probability of a distribution. This is basically the chance of two independent samples having the same value. And we know that if we consider all distributions over domain size N, then the one to minimize it is the uniform distribution over the entire domain. But a little bit more interesting fact is that any distribution that is epsilon far actually has a noticeably higher collision probability, okay? And we're going to use this gap in order to test uniformity. So our idea is going to be to estimate the collision probability and to say yes, to say uniform if it is low, and to say not uniform if it is high. So how are we going to estimate the collision probability? The basic idea is that if we draw two samples and compare them, then, well, they will be the same with exactly the collision probability. So this indicator actually has the right expectation, but of course it doesn't concentrate well because this is only one indicator. If we take a bunch of samples and make a bunch of comparisons, then actually we get a good concentration. So this is the statistic that we take. We count the collisions among Q samples and we normalize by the number of comparison, which is Q choose 2. Let me just say that these indicators are not independent, and this is kind of the problem, the reason why the first original analysis wasn't optimal. So this is a bit tricky. The dependencies create some problems. Okay, so let me give you some motivation for this. So for our results, lately testing was considered under many constraints in many models. So it started roughly 3 years ago, as far as I know. There's been a whole bunch of work on that. And what motivates us is that under constraints, the original tester counting all the collisions among batch of samples is irrelevant. This kind of makes us a bit sad. So our idea is to generalize this tester, the collision-based tester, and we do it as follows. So here's a new definition. we call a comparison graph. And the idea is this: we refer to all of our samples as a bunch of vertices in the graph, and each edge in the graph is a comparison, a pair of samples that we actually compare. So now we have a collision indicator, such as before, for each edge in the graph, in the comparison graph. And the new statistic is going to sum the collisions, so to count collisions only between pairs of samples that are indicated by the comparison graph. So we sum these indicators only over the edges of the graph, the pairs of samples indicated by the graph. And of course, we normalize by the number of comparisons we've made. And this should estimate the collision probability. So again, if this is low, then we say uniform, and if it's high, we say not uniform. Okay, so let's see some examples of the duality between a collision-based tester that is induced by a graph. So the original tester is to compare all the pairs of samples. So this is basically a clique graph. Another possibility is to divide all our pairs into two batches and count collisions only between the two different batches. This would be actually represented by a complete bipartite graph. Another possibility is to say ditch the entire dependencies that we said that this clique creates, and to draw a completely new pair for each comparison that we make. And this would be like a perfect matching. Okay, so I hope this gives you some notion of the duality between comparison graph and the collision-based tester that they induce. So here's our first structural result. A comparison graph induces a good n-epsilon uniformity tester if it holds, if two conditions hold. And let me just remind you that n-epsilon uniformity tester distinguishes between the case that we're uniform over the entire domain of size n and the case that we're epsilon far in L1 distance. Okay, so the two conditions that the comparison graph must hold is that it makes enough comparisons, so the number of edges should be large enough as a function of n and epsilon, but also that it creates relatively few dependencies. So dependencies here, as we said before, dependencies are quantified by two paths in the graph. So each time we have two comparisons that share a sample, this created two paths, and these are bad for us. They increase our variance and they make the concentration not as good, and this is bad for us.
You have a minute left.
Okay, so this is the idea. And in particular, if we look at the clique graph, then whenever this is the size of the clique, then those two conditions hold. Okay, so let's see how we use this to create uniformity testers under constraints. So this is the generic recipe. We have the tester requirements and we have the constraints by the model. We also have a complexity measure which might vary from model to model. And we basically want to translate all of this to graph notations, okay, to understand to some constraints, or maybe the value that we want to optimize, the measure is the value that we want to optimize, or the comparison graph. So we use theorem 1 in order to translate the requirements of the tester to the graph constraint. This is exactly the theorem that we said. We need some structure on the comparison graph. And we will need to use some heuristic that are model dependent to understand the other two. But once we have everything in the language of graphs, we simply need to choose the right comparison graph and simulate the tester that it induces in the model. So let me give you one example. I probably won't manage to do two. One example is that we have a simultaneous model. So we have k players, each of them get q samples, and they can only send a short message to the referee, but they cannot interact with one another. So this is the constraint of the model, and we count how many samples per player are required. So as before, this theorem tells us that we have this constraint on the graph, but also since we have k players that can't interact, then the graph, it represents the entire set of samples, and it's actually made of k disjoint subgraph. Each subgraph is the set of samples of a single player. And the sample per player, well, this is the number of nodes in each subgraph. If we take all of this and match them up together, then it's quite clear that each player needs to take q samples and compare all of them together, and only send the number of collision it sought to the referee. So this is a small calculation that I'm going to skip. Let me just say what is the streaming model. So in the streaming model, we have the samples come as a stream, and we only process one sample at a time, but we can store up to m samples. And we have this cute lemma that says that this also gives some constraint on the graph. The average degree of the comparison graph cannot be too high. And it's quite surprising that the best comparison graph for this model is also the same graph as before, only with different parameters, of course, regarding to the model. So let me just sum up real quick. We generalize the notion of collision-based tester using the definition of comparison graph, where the edges simply indicate which comparison we're going to map. And we showed some generic recipe for uniformity testing under constraints. And it actually induces optimal or near optimal results in several known models. And we hope that it can also help devise more testers for uniformity testing in other models. So that's it. Thank you. Sorry for going over time.
No worries. Thanks, Avi. So let's go over to the next speaker. Okay, yeah. So next speaker is Jay Mardia.
Hi. Should I begin?
Okay. So Jay is going to tell us about the gap between, or maybe there's no gap between the detection and the recovery complexity of planted Clique. Okay, Jay, go ahead.
Yeah. Thanks, Anannya. So I'm Jay Mardia, and let's just dive in. Let me start by telling you a little bit about the planted Clique problem. It's a problem on a graph with n vertices, and the second parameter k, which you want to care about, is the size of the planted Clique, but don't worry about the details. And there are two variants of this problem, the detection variant and the recovery variant. I want you to think of k as being some sort of a signal to noise ratio, because this is a statistical problem, and as k becomes larger, the problem becomes easier. In fact, if k is larger than 2 log n, then we know that information theoretically, both the detection and the recovery variants are solvable. That's great. However, we only know of polynomial time algorithms to solve these problems if k is much, much larger, on the order of square root of n. And in fact, decades of research has solidified the belief that this is indeed the best we can do. And there is an exponential gap between the signal to noise ratios at which this problem is statistically versus computationally tractable. This sort of a gap, called a StatComp gap, is believed to exist for a wide variety of problems, not just this one. On the previous slide, one thing that was implicit was that we equated computational efficiency with the existence of polynomial time algorithms. And I'm sure I don't need to justify this. I think everyone here will believe that that's a reasonable thing to do. And the study of StatComp gaps has also taken this perspective. However, we know that there are other useful notions of complexity. They consider other resources that are different from time. And also, studying them sometimes gives surprising insights. For example, the space complexity turns out to be related to the complexity of two-player games. Communication complexity turns out to have connections in understanding streaming complexity. So studying these can be surprising. Further, perhaps implicitly, the study of these StatComp gaps implicitly already knows this. The evidence for the planted Clique conjecture that I told you about on the previous slide has built up by studying restricted algorithmic classes and showing that these restricted classes can't solve the problem below the square root n threshold. If we squint a little at these things which study the levels of a convex hierarchy or the degree of polynomials required to compute certain things, we can imagine that they're studying non-standard notions of resource or complexity. And so implicitly, in the statistical context, these non-standard alternative notions of complexity already are being studied. And so the point of this slide is just to try and convince you that maybe we should explicitly start studying these. And if we do, then at least I think the first thing we should try and do is see if this StatComp gap that existed still exists. What if it disappears? What if the location at which these thresholds appear changed dramatically? So basically, what I'm asking is, are these StatComp gaps fundamental to the problem, or do they depend quite heavily on the notion of computational efficiency that we are viewing them through? Obviously, these are very broad questions, and in this work, we don't answer any of them. We just look at one specific notion of alternative complexity and one specific problem and try to see what happens when we put them together. And so what we want to do is see if the StatCom phenomena that we know and love for the planted Clique problem also hold when we use the length of space complexity. Okay, and what are these phenomena? I already mentioned that there is this statistical computational gap that exists. And what I haven't told you so far, but is true, is that the detection and the recovery variants of this problem have the same complexity, at least when we view it through the lens of polynomial time algorithms existing or not. It's the exact same threshold at which polynomial time, signal to noise ratio threshold at which polynomial time algorithms begin to work. And so our hope is that even for space complexity, this sort of phenomena holds. Just so we're on the same page, by a space efficient algorithm, we mean an algorithm that takes roughly O of log n bits of space, or working space, or scratch paper. Okay, what are some easy to see facts about the space complexity of this problem? In fact, if we simply analyze existing algorithms for this problem, it's very easy to see that detection can be solved efficiently or in O of log n bits of space as soon as k is larger than the square root n threshold. This is exactly what we wanted, and so far things are great. However, all of the existing algorithms for recovery seem to require polynomial amounts of space. And so the question here is there actually a log space algorithm to recover planted cliques of size larger than omega of root n? If we can come up with such an algorithm, the nice thing is that the conjectured time complexity based StatCom gap at this threshold would also hold for space complexity at the same threshold. And even for space complexity, we would know that detection and recovery are the same for this problem. They behave essentially identically. What this would do is this threshold signal to noise ratio of omega of root n would now, we would believe it is indeed fundamental to the problem. It's robust to changes in our notion of efficiency, and it's robust to changes in like what formulation we use, detection or recovery. So this is why we want a log space algorithm for this problem. This is what we're aiming for, and the main result of this work does not give us what we want, but it comes fairly close. What we can do is design an algorithm that has this ugly looking space complexity bound. The log star function is like extremely slowly growing function. And just so we can understand this bound a bit better, let's look at some examples. If the signal to noise ratio or clique size k is just slightly larger than square root n, I think those are 9 logs stacked on top of each other. 9 is arbitrary. It could be any constant number of logs stacked on top of each other. If this was the clique size, then the space complexity of this algorithm would indeed be O of log n bits, which is exactly what we wanted. However, if we really do go down to the square root n threshold, precisely there, then the space complexity is log star n times log n, which isn't exactly where we want it to be. It's slightly off. However, it is really close, and what it does is suggest that a log space algorithm that we want exists, and hence maybe the phenomena that we want for space complexity also hold. I'll end by just mentioning a couple of open problems. The first is the obvious one. Is there a log space algorithm for this problem at the root n threshold? And the second is a more vague and open-ended open problem, which is we wanted to study the notions of, we wanted to study the StatCom phenomena for our various problems with alternative notions of complexity. But here we've done this only for one specific problem and one specific alternative notion of complexity. It would be very annoying to have to do this for every single problem where we already know a StatCom gap. So is there a more generic way in which we can study all large classes of these problems? I have a few seconds, so I'll just plug. On the Slack channel corresponding to this paper, I have a poll, and you can go and opine whether you think that this log space algorithm actually exists or not. And yeah, thank you.
Thank you, Sheikh. So maybe, and will you, and after the opinion poll is done, will you tell us about a new result which achieves the log space algorithm?
Yeah, I think democracy will prevail, and then we don't need to prove anything, right?
Okay. Okay, great. Thank you. So next up is Pascal, who is going to tell us about finding Hamiltonian cycles with high probability. So Pascal.
All right, so I'll jump right in. Hello, everyone. Thanks for coming. My name is Pascal Su. I'm from ETH Zürich, and this is joint work with Rajko Nenadov and Angelika Steger. So this is that session on graph algorithms, so I probably shouldn't explain too much on graphs, but just for completeness, so we know a Hamilton cycle is a cycle which visits every vertex in a graph. And to find Hamilton cycles in graphs, this is generally viewed as a rather hard problem. So this is a NP-hard problem, and it would be very surprising if we find a polynomial time algorithm for this kind of problem. So in general, we know this problem is hard, but is it also hard in very specific cases? And the answer is, of course, no. Already very early, we had Dirac's theorem, which told us that if the minimum degree is n/2 in any graph, then we can find a Hamiltonian cycle. So intuitively, if the vertices have a lot of edges, then, well, surely there is some substructure there. And the proof of this theorem, this works via Poisson rotations. You might be familiar with them. The idea is if we have a path and we have an edge going back to the path, then we can replace the corresponding edge in the path to get a new endpoint of the path. So we have a path with the same vertices, but a different endpoint. And this allows us to, let's say, search for a continuation of the path for a very long time. And with this method, for example, Dirac's theorem can be proven. Okay, so let me talk more about random graphs. We have the Erdős-Rényi random graph model, which you might be familiar with. This is a graph on n vertices where every edge is present with probability p independently. So if we look at Dirac's theorem, we immediately see, okay, if we have a gn 1/2, a little bit more than 1/2, simply by concentration bounds, okay, this graph must be Hamiltonian because every vertex has degree at least n/2. Right, so then the question is naturally, is this the best we can do? And it is not. For random graphs, this is a very well-studied problem. And we know even the lower order terms for which are needed, such that GNP is Hamiltonian. So this is roughly P, which is log n over n. So as soon as we have, on average, log n many edges, we should have a Hamilton cycle in our graph. And this threshold coincides with the minimum degree 2. So as soon as GNP has minimum degree 2, we also expect it to have a Hamilton cycle. And of course, not any sooner, because as long as there is a edge with only one edge, a vertex with only one edge, this vertex cannot be part of the cycle. Okay, and this is kind of part of the intuition that says that randomness really helps a lot with the expansion properties to find these Hamilton cycles. And there is a lot of existing work on this that kind of proves that in random graphs that Hamilton cycles are present, not just a few, but a lot of them as soon as we have at least one. And taking this intuition, maybe we can build an algorithm. So we cannot hope for an algorithm in the general case that can find a Hamilton cycle in any graph, but maybe we can find a Hamilton cycle in most graphs, or at least in a random graph. So maybe let me give you a quick overview on what has been done so far. This is just a short outtake. By no means is this complete. So the first 3 results, maybe you can see that the focus was on improving the P at which we could find Hamilton cycles and less the runtime. But the runtime was always polynomial, which is significant for the P versus NP question. And in the later 3, these results were actually done in the adjacency matrix model. And there, this time here is optimal, but the P is by no means near this threshold yet. So there was still some work to do, and this is where we would like to improve upon this. So we would like to go in linear time, at least at the same P that the first algorithm here, the Angluin and Valiant algorithm, was working at. So let me give you a bit of an intuition how our algorithm works. Or let me actually start with the original algorithm by Angluin and Valiant. Because I said that in random graphs, we have so much structure, we have a lot of expansions, we can find a lot of Hamilton cycles. And the first intuition is just we want to do a random walk. So if I start from any vertex, I can query a next edge at random, and then with high probability, I'll get some new edge which is currently unvisited. And I'll do this for a while, and you can see as long as my pass is very short, the number of vertices which are still used is very small, and the number of unused vertices is very large. So with some constant number of new queries, I can just increase the length of my pass. So I can do this for a while, and at some point, my pass will cover most of the vertices, and then there comes a problem that I might need to query a lot of new edges at the single vertex, and this might not be good because a random graph will, on average, only have log n many neighbors. So what I can do here is implicitly do the polar rotations I mentioned at the beginning. So if I query new edge, then if I'm going back into the pass, I ignore the edge if the distance to the current vertex is less than n/2. And if it's more, then I can detach the cycle in this way. And then I get a new starting point from which I can try to continue my pass. If at some point I find an edge back to the cycle, I can reincorporate the cycle into my pass. And this way, I mean, if I'm a bit lucky, then hopefully this random walk will find all the unused vertices and eventually give me a Hamilton cycle. But as you could see, towards the end, most of the vertices are already used. So the probability of finding a new vertex is very small. And this is going to be the bottleneck. And this is where we will actually improve upon the original algorithm. So if we do a short analysis of this, what we do is just we query random edges. So the probability of finding an unused vertex is exactly the number of unused vertices divided by the total number of vertices. So this is equivalent to the coupon collector problem. And there's a bit of a technical detail why there's an additional log factor, namely to store the pass and do these polar rotation, we need a data structure which accumulates an additional log n factor. So this was the original algorithm by Angluin and Valiant, and the runtime of this was n log squared n. So we try to shave off these two log factors with a neat trick, and maybe this can be helpful also for other algorithms which need to speed up down to the optimal runtime. So the first thing that we do.
Yeah, we have a minute left.
Okay, thank you. The first thing that we do is instead of, because I said there's this technical detail of polar rotations, the first thing that we do is we look for a matching instead of a Hamilton pass. The reason for this is if in the matching we replace edges, this is a local change and we do not need to change anything on the other edges. And as we can see here, the local change does not affect the other edges, so it can be stored in constant time. And the second part that we wanted to improve was that towards the end of this matching that we kept on having less probability of actually finding. So, so I'm going to skip ahead a bit. So at the beginning, it should be easy to find new edges because we choose random new neighbors, and these should not be used yet. But towards the end, the target set might shrink a lot. So what we do is expose a neighborhood of this target set, like this, and then any neighbor of the target set, any matched neighbor to these vertices is also a good neighbor because we can then replace two edges, one edge with two edges. So what does this mean? If we search for a new matching edge from a vertex in B, then we have now we could match to the target set, which is of course good, but we can also match to these neighbors of the neighborhood of this target set, and then replace the blue edge here with an orange and well with two orange edges. And in this way also increase our matching. And if as long as this neighborhood is large enough, then we guarantee that the probability is big enough to finish quickly. Okay, and there are some technical details to if we get two perfect matchings, we get a bunch of cycles, and these cycles can then be stitched together to a Hamilton cycle in reasonably fast time, so to keep the whole algorithm linear. And so this is what our work was. And I'm sorry that I had to speed up a bit at the end. If you want a closer look at the algorithm, take maybe a look at the longer talk or at the paper that we published. Thank you.
Thank you, Pascal. So next up is Gopinath Mishra, who's going to tell us about streaming models. So
yes, so
Pascal, I think you have to stop screen sharing.
Yes.
Great. Yeah. Great. Go ahead.
Thanks, Ananda, for the nice introduction. This is Gopinath Mishra from Indian Statistical Institute. I will talk about even the easiest graph coloring problem is not easy in streaming. This is a joint work with Anup Bhattacharya, Arijit, Bishnu, and Anannya Upasana. In this paper, we consider a simple variant of classical graph coloring problem in streaming model. The problem we name it as conflict estimation problem, where we have two inputs, the graph G itself and a coloring function f on the vertices of the graph. The objective of us is to estimate the number of monochromatic edges in the input graph with respect to the given coloring function f. First, observe that this conflict estimation problem is very easy in classical RAM model. Also note that this is the problem we consider, this is the problem whose a easier variant or further simpler variant we use to prove that the classical graph coloring problem is in NP. In this paper, we study this so-called easy graph coloring problem in RAM model in different vertex arrival streams. Let us have a brief discussion what are different vertex arrival streams. In the basic vertex arrival streams, the vertices of the graph is exposed in an arbitrary order, and for us also with their colors. When a vertex V is exposed, we also get to know all of its neighbors that are in the pre-exposed vertex set. Vertex arrival with degree oracle, in short, VA-DEG model is same as that of vertex arrival model, but we also get to know about the degree of the vertex V when V is exposed. There is another vertex arrival model called vertex arrival in random order model. The random order in VA-RAND it is same as basic vertex arrival model, but the ordering in which the vertices are coming, say V1 to Vn, corresponds to a random permutation of 1 to n. This is our set of results. We study the conflict estimation problem, where our objective is to estimate the number of monochromatic edges in all three vertex arrival models. In this slide, n denotes the number of vertices, m denotes the number of edges, and the capital T denotes a promise on the lower bound on the number of monochromatic edges. Note that in VA and VA-DEG model, the upper bound and lower bound is tight. And the space complexity for conflict estimation in random order vertex arrival model is better than that of other two. Also, note that there is a gap between upper and lower bound in case of random order vertex arrival model, which again I will discuss around end of the talk. Also, I would like to note that our main technical contribution in this paper is upper and lower bound in case of random order vertex arrival model, which I will present in this talk. So let us first discuss the proof sketch of our upper bound result for conflict estimation in random order vertex arrival model. First, observe that the number of monochromatic edges in G with respect to F is half of sum of monochromatic degrees of all the vertices. Our idea in a high level is to pick a random subset of vertices R of desired size, say n by root t, and note that this R for us is fast n by root t vertices in this stream, because now we are discussing about random order stream. The idea is to examine the neighborhood monochromatic
Gopinath, we can't hear you.
context we have inside this set R plays a very important role in the design and analysis of our streaming.
Gopinath, last 30 seconds got cut off. So maybe you can go back for the last 30 seconds there. You weren't audible.
Yes. So shall I repeat this slide? Yes, sure.
Yeah. The slide. Yeah. Can you please repeat the slide?
Yes. So was the previous slide okay?
Yes. The previous slide was okay. This one, the end.
Okay. So our idea in a high level is to set R. Also, the main idea is to examine the neighborhood of every vertex, the monochromatic neighborhood of every vertex in this randomly selected set R. So the quantity kappa V, which is the number of monochromatic neighbors V has inside this set R, we call it as projected monochromatic degree of V, play a very crucial role in design and analysis of our algorithm. And the main observation is this quantity kappa V can be computed in the stream, in the vertex arrival stream, because the set R is the first set of n by root t vertices. We start the algorithm by storing the colors of all the vertices in the set R, and we are considering vertex arrival stream. So the projected monochromatic degree of any desired vertex V can be computed in this stream. Now let us have another observation. Consider a vertex having large monochromatic degree. Observe that the projected monochromatic degree kappa V is good enough to estimate the monochromatic degree of the vertex V, as monochromatic degree is large in this case. But note that the challenge is, how can we decide a vertex is having high monochromatic degree? Because we are seeing the graph in a streaming fashion, so graph as well as the coloring in a streaming fashion. So we cannot know whether the vertex is having large monochromatic degree for all the vertices. So to cope up with this, our idea is to classify the vertices as high or low depending on the value of projected monochromatic degrees, that is kappa V's. And this can be done because we have already discussed this kappa V, quantity kappa V's, that is projected monochromatic degrees, can be computed over random order vertex arrival stream. So our idea is to classify the vertex set of the graph into two parts, namely capital H and capital L, where H denotes set of all high vertices and L denotes set of all low vertices, and break the sum of monochromatic degrees into two parts. It is sum due to all high vertices, and the second part is sum due to all low vertices. And we will be done by discussing how to approximate MH and ML namely. So
try to wrap up in a minute.
Yes, sure. So this is our idea to approximate both MH and ML individually. So we have already briefly discussed about how to approximate the quantity MH by classifying depending on the value of projected monochromatic degree. And to approximate the low vertices, the projected monochromatic degrees won't be good enough. That's why we apply a bucketing technique where estimating the size of large buckets will be good enough. And as we are considering vertex arrival stream, and we are storing all the vertices as well as colors of all the vertices in R, we can compute, we can also estimate the sizes of the large bucket. And the space complexity is dominated by the size of R, which is roughly n by root t. And here we would like to note that we also prove a lower bound n by root t, n by t square, which is not tight, by reducing from a variant of multi-party set disjointness. However, we believe that our upper bound is in fact tight, though we don't have a proof. Thank you everyone for listening to the talk.
Thank you, Gopinath. So the last speaker is Nitin. So Nitin, if you can share your slides, please.
Can you see my screen?
Yes, we can.
Okay. Here you go. Hi, I'm Nitin Verma. I'm a postdoc at the University of Haifa. And today I will speak about erasure-resilient sublinear-time graph algorithms. The goal of our paper is to model and investigate sublinear-time algorithms that run on graphs with incomplete information. Usually in the case of sublinear-time algorithms for graphs, the assumption is that you have query or sample access to graphs. And this is not realistic in many scenarios. For example, consider the case of a social network where vertices are users and edges denote the friendship relations. And for privacy, some users could decide to hide their edges, and we get a partially erased graph. Such partially erased graphs could be represented as adjacency list model, where there are erased entries, erased adjacency entries. Specifically, and for a constant alpha, a graph is alpha erased if at most alpha fraction of the entries in the adjacency lists are adversarially erased. A completion of such a partially erased representation is a valid graph obtained by filling in these erased entries. This is an adaptation of the erasure-resilient model for function property testing to the case of graphs. Now, an erasure-resilient graph algorithm gets a parameter alpha and query access to an alpha erased graph. It can make two kinds of queries. It can specify a vertex and ask for its degree. It can also specify a vertex and an integer I and obtain the ith entry in the adjacency list of V. And this entry could be erased, for example. The performance of algorithms are analyzed in the worst case over all alpha erased graphs. And we study two important computational tasks, that of graph property testing and that of estimating graph parameters. In the context of graph property testing, our model can be seen as a generalization of the general graph model of Parnas and Ron, which is in turn a generalization of the bounded degree graph model of Goldreich and Ron. In particular, we study the properties and problems of testing connectedness and estimating the average degree. So this is the kind of schema of the problem of erasure-resilient testing connectedness. There is an algorithm called the tester that receives two parameters, alpha and epsilon. It has query access or oracle access to an alpha erased graph. And the requirement is that the algorithm has to say accept with probability at least 2/3 if there exists a completion of this graph that is connected. It has to say reject with probability at least 2/3 if for every completion you need to add at least epsilon m edges to make it connected. And in this case, we say the graph is epsilon far from connected. Now, this is a meta definition, and this can be generalized to other properties also. In the special case of no erasures, connectedness testing has already been studied, and the prior best tester has query complexity 1/epsilon d squared, where d is the average degree. And here are our results. We say that connectedness testing is not so easy always, specifically when the fraction of erasures is more than a threshold. Here, the threshold is the proximity parameter. We say that connectedness testing requires a number of queries linear in the input representation. On the other hand, we say that if alpha is smaller than this threshold, then we can test connectedness in using number of queries independent of the length of the input representation. further, we show that if alpha is even smaller than epsilon over 2, we can further improve the query complexity. So these are the somehow like big things that like at a high level, we show a phase transition that there is a fraction of erasures above which connectedness testing requires linearly many queries, and below connectedness testing can be done in constant many queries. In the special case of no erasures, the complexity of our tester is better than that of the best prior upper bound for this really well-studied problem. And our upper bound is also tight, as we show in a later work. For average degree, this also has been well-studied. And specifically, Feige showed that one can obtain a 2 plus epsilon approximation algorithm by making only root-n degree queries. And he also showed that to get something better using only degree queries, you need omega n query complexity. Now, in a sequence of work, Goldreich et al. And Eden et al. Showed that one can obtain a 1 plus epsilon approximation algorithm that makes roughly root-n degree and uniformly random neighbor queries. And this is what we show. We show that estimating average degree of alpha erased graphs can be done with approximation ratio 1 plus epsilon plus 2 alpha using query complexity root-n. And we show that this presence of alpha here is in some sense necessary, that if you want to get like 1 plus gamma approximation for gamma less than alpha, you need to make at least omega n queries. And our model can be seen as an interpolation or unification of the model with only degree queries and the model with both degree and neighbor queries. Specifically, when alpha is small, or say 0, we have access to both degree and neighbor queries. And as adjacency list entries get progressively erased, you can view this as like losing access to some of the neighbor queries, and you are in the model by Feige. So here are a bunch of open problems. So we saw that there is a phase transition in the testing connectedness. Now, there is also somehow a secondary phase transition, much softer, around alpha is equal to epsilon over 2. Is that inherent by any chance? Now, a graph property is monotone if it is preserved under deletion of edges and vertices. And it's a large class of properties. And we observe that if there is a bound on the vertex degree, then one can obtain erasure resilience in this adjacency list model by paying only d square in the query complexity. We ask, like, what is the cost of obtaining erasure resilience for testing monotone properties for general graphs, which is what we've been considering in this paper. Our model for formation of erasures is quite general in the sense that a vertex V can be erased by an adversary from the adjacency list of U, but U can still be present in the adjacency list of V. We ask whether testing can become easier if one assumes that erasures are somehow made symmetrically. In the sense, if V is erased from U's list, then U also is erased from V's list. This is an assumption, and can this assumption make life easier? Like we also, this is another interesting question, the relationship between erasure-resilient and tolerant testing of graphs. Roughly speaking, a tolerant tester for a property must distinguish with high probability between inputs that are somehow close to satisfying a property and inputs that are far from satisfying a property. Dixit et al., who introduced the erasure-resilient function property testing model, showed that for testing properties of functions, a tolerant tester implies an erasure-resilient tester up to some parameters. And their technique actually does not work for the case of graphs. And so for the case of graphs, this relationship is somehow much more unknown. So what is really the relationship between having erasures in the graph versus having maybe wrong entries in the adjacency list? Or rather, what is the relationship between erasure-resilient and tolerant testing in the general graph model? So lots of open questions, and thank you.
Thank you, Nitin. And thank you to all the speakers in the session. So we ran a little over time within the session, but that was good. So now let's, the idea is to have a panel have a open discussion. If there are any questions from the audience, we can start with those. Otherwise, I have some questions. You can, if you're a panelist, you can just unmute yourself and ask a question. And otherwise, if you can just message a question. Okay, if not, then let me get started. Let me ask the questions. My first question was to Uri, actually about the uniformity tester. So you proposed a unified analysis based on compare these conflict graphs. Do you think there might be something along the same lines for a general problem of identity testing?
Oh, yeah, so great question. So basically, I didn't say this because it was a short presentation, but identity testing can be reduced to uniformity testing. So all of our results apply for identity testing as well.
Okay.
So, yeah,
Okay.
Great question for this short talk.
Okay, excellent. Okay. Another question. Okay, so maybe I can I can just go over to each of one question. First of all, for some other papers, and then we'll see how much time we have. I had another question actually about the last presentation, Nitin. So
Yeah.
I guess in the dense graph model, we know of good, like, these kind of some universal results somehow for tolerant property testing, right? With the evasion noise, I guess, could one potentially hope for even more general results, given somehow the evasion noise is a little, in the dense graph model, given it's even somehow weaker than, like, adversarial corruption noise?
In the dense graph model, so erasures are slightly less problematic, I would say, than the adjacency lists model, because it's a functional representation, and this already falls under the purview of like the function property testing, a model, the erasure model that we defined, and again, so tolerant tester would imply erasure-resilient with tester with comparable complexity.
I see. No, but I was wondering, like,
if you encounter an erasure, you can, well, there is a question of consistency, but okay, there is a mild assumption here that I'm maybe assuming that I have access to 1/2 of my adjacency matrix, but more or less, you can just substitute this erasure with like a 0, and this is okay.
Okay. Yeah, I was thinking more along the lines of these results would say there's isn't it this result that if a graph is a hereditary property, if hereditary properties can be tested with constant query complexity even under noise or something like that, right? I was wondering if, like, there are such universal theorems,
I think they will apply for, I think they should apply for erasure resilient testing also. Yeah.
Okay. Are there any other questions from any of the panelists, any of the audience?
Maybe I can also ask a question to the last speaker. So did I get this correctly? You assumed that the adjacency lists were like permuted randomly?
Not randomly, adversarially erased. Some entries were adversarially erased. Some adversary, before the algorithm interacts with the graph, some adversary comes and erases an alpha fraction of the entries, arbitrary entries.
But the adjacency list, like, are the entries like sorted, or is the adversary also allowed to sort like the non-erased entries?
So adversary has no control over the ordering of adjacency entries, and we do not assume anything about the ordering of adjacency entries as well.
So in a sense, you're also assuming that it's adversarial, right? If you don't assume anything.
Yeah, right.
Would it help in any way that it's sorted, or does the problem become trivial if it's sorted in any way?
No, I do not think so. No, but it could help. It could help, but I do not think the problem, at least the connectedness, no, I don't think it would become trivial. No. But there could be problems that might become trivial, but not the problems that we are considering. Good question. Thank you.
any? I mean, I have a, okay. Sorry, there's a okay. Sham, I can. Okay, Sham has a question to Jay. That is it known that there is a randomized algorithm that finds the planted clique in log space? It seems to me that de-randomization would be non-trivial even in the random graph case. I guess he's asking about a random graph setting. Uh, Sham, maybe I can let me see where
Oh,
Sham is.
actually, sorry. Basically, my
Oh,
question is: it seems like my understanding is this algorithm is deterministic, and it finds it in whatever log n, log star n.
Yeah. You're right.
But I'm wondering, like, is it possible that there could exist like a like if you're allowed arbitrary randomness, could you find a log space algorithm?
Yeah, it's a good question. When I was looking for such an algorithm, I didn't restrict myself to deterministic algorithms. I was very happy to use randomness if it helped. I couldn't find a way to use it helpfully, but you're absolutely right. It might be a good avenue to try and see if you can use some techniques that necessarily need randomness.
Okay, cool. Thank you.
I mean, generally also like, I guess, I mean, this doesn't have any bearing on the question you asked, but this gap that is there between a potential randomized deterministic potential speed up obtained due to randomization, I guess it's really tiny for any de-randomization kind of things to work really.
Sure.
So I guess it, yeah, it doesn't have any bearing on the question really. I mean, I guess I also actually, I mean, it's a good time. We can have this discussion continue. We can continue this discussion, but it's a good time to remind everyone that the other session is starting as well. So in a couple of minutes. So if you want to go there and miss this exciting discussion. Okay, so actually, I also had another question for Jay. So you talked about the statistical computational gaps. I guess planted clique is an instantiation of the denser subgraph problem. Or like, one can think about like, problems where even like, we know tight upper and lower bounds like stochastic block models. So there isn't really like per se, like at that level for the vanilla stochastic block model, there isn't a gap. But I was just wondering if you have thought about like, more general versions of general questions like these.
Yeah, so I haven't explicitly thought about them for too long, but let me address the two examples you did give. So I think even for the stochastic block model, I think when there are more communities, like there is some sort of a gap, and even just when there isn't a gap, you could ask the question: okay, we have polynomial time algorithms. Do we have log space algorithms?
Mm-hmm.
Without explicitly thinking about this too hard, I think that they should follow fairly easily. Because there are spectral algorithms, and in the stochastic block model, the input graph is sparse. And so you should be able to do some sort of local walk. And so some of the real struggle in the planetary clique problem with getting the complexity down from log square n bits to log n bits is that the graph we're concerned with is not sparse. And so I expect that for sparse graphs it should be fine, but don't hold me to that.
Actually, on that note, so when you say you have sorry, I should have asked this during the talk. When you say you have a log space algorithm, you just mean that you will output the identity of one vertex after another in a logarithmic space, like some sort of a. Okay.
Good question. There wasn't enough time for me to specify the details, but the tradition in any space-bounded computation framework is we only count the sort of working space against our space bound, and the input is provided like on a read-only piece of paper, and the output is on a write-only piece of paper, and that way you can output pretty large things.
Fair enough. Good. So okay. So standard complexity model of there is a work tape, but the output tape you're not going to count. You cannot generally write. Okay, great. So along those lines, maybe one more question. Really, actually, sorry, I should let others ask questions if there are other questions.
I have a question for Jay.
Oh, okay.
So what other problems, like other than like planted clique or recovery or detection, what other problems where you see this like stat comp gap and you can explore for other computational resources?
I think Anannya mentioned something called the tensor subgraph problem. So I think the tensor subgraph problem is hard for me to keep in my head because there are too many parameters to keep straight. But I think for certain parameter regimes, there is some sort of a stat comp gap. And the other problems are things like sparse principal component analysis, tensor principal component analysis, and yeah, these sorts of statistical-ish problems where you also want to impose sparsity. These sorts of problems somehow seem to have StatCom gaps in them.
Okay.
If you want to see the entire web, I would recommend looking at this paper by Brennan and Pressler from MIT, and yeah, they sort of find a nice web of reductions between various problems.
Okay, thank you.
Other questions? Well, if there are no other questions, I can continue with my questions. So actually, another question was for Gopinath. So can you go back to your slides again, actually?
Yes,
Can
sir.
you share your slides? Yeah, that would be great. So because yeah, there was a crucial point when you got cut off like for the second time. So sorry, I missed actually the notion of approximation you talked about. Was it a multiplicative approximation? Was it an additive approximation?
It is in multiplicative approximation.
Multiplicative approximation. Okay. And secondly, so you talked about a very basic, like, I guess, binary relation, estimating a very basic binary relation.
Yes, yes.
Is there something like one can ask something similar as a ternary relation? Like, if there was a hypergraph and you were asking how many monochromatic three hyper edges were there?
Yes, that is a nice question, but we tried, but it needs more thing to be handled in the stream, because handling observe that in streaming, estimating number of edges is direct, but the triangle problem, even if uncolored version, is non-trivial.
I see.
So colored version of triangle is maybe our future work. But even if we don't know if what is a normal triangle counting, if edges are coming in random order.
Okay.
Or so even if uncolored version in random order stream are not solved. So
well, I was thinking of, I was not actually thinking about, like, that you are given edges and you're going to do triangle counting. Maybe maybe my question is not very sensible, but the question I was asking is whether one can ask whether, like, if you were getting hyper edges as your input itself,
yes.
then
Yes.
would it,
So
yeah.
yes. So suppose in that case also, that is a nice question, but the difficulty will be at this step that consider a three uniform hyperedges UVW. Here we are considering vertex arrival model. So we get to know about this hyperedge when the last vertex arrives.
Okay. I
And
see.
To check whether this is monochromatic, we need the colors of all three, where the challenge lies.
I see. I see.
So the middle vertex supposedly will try to create problem, it seems. So.
Sorry, there was a question from sorry,
Yeah,
your
hi.
screen. Yeah, go on.
Yeah, hi. I had a general query with respect to extending these algorithms to function approximation settings. For example, applying some sort of uh, uh, networks or deep layers or hierarchical structures, and adding some kind of a stochastic noise here for the sampling. So I was thinking more in terms of ML, and how will that help for the future generalizability if we look at from that viewpoint.
Yes, the algorithm can be adapted for to estimate number of a particular kind of constrained edges, so colorful edges or satisfying some kind of color combination. that suppose we are allowed with some k colors and the color difference will be something or other, that the difference would be large or for those settings this problem can be adapted, but adding noise I am not sure, so whether our technique can be adapted or not, but that will be a nice question to study.
Cool, thanks.
Other questions? I actually had one more question. So for Pascal, so sorry, I'm not very familiar with the random graph literature, but you are there examples of other similar NP hard search problems where on random graphs such sharp thresholds are known and there are efficient algorithms but not necessarily linear time algorithms? Apart from Hamiltonian cycle, is there something one can think about or potentially apply your ideas to other graph problems, something like that?
Let me think. Well, so I mean, so there's approximations for graph colorings and independent sets. I mean, that would be like the natural NP complete problems I could think of, but they're actually not. I mean, it's very hard to estimate precisely like what is the size of or what is exactly the colorability, but it's very well known, like some ranges, like that's very well studied. But and there, I guess there exist some algorithms which also do some greedy type strategy and then do some adjusting. I would assume that, yeah, so I think they're not optimal yet, but they're also like the bounds are not optimal yet. So I guess that's always work. And then I guess there's not, or I can think of another natural NP complete problem on graphs, I guess. I mean, structural wise, yeah, anything like a Hamilton cycle is maybe not natural enough to, I mean, the Hamilton cycle makes most sense, I would say.
I guess because many random, yeah, I'm trying to think because many constraint satisfaction problems or something like that for random settings, I guess the answer would probably be something which concentrates around something. I'm just trying to think what are the search problems one can think about. But yeah, I guess Hamiltonian cycle independent set is a natural choice.
I mean, randomness tends to always help a lot. This is what I've been able to observe. But
follow up then. Will the avial trees also help here with respect to randomizations?
Can you repeat the question?
The avial trees.
Yes. What? Yeah.
With respect to those randomizations.
So I don't know. So do we use avial trees or?
Specifically with respect to those randomizations, as you said, in high dimensions. So I was just thinking, if we apply that data structure, those trees, that might help with respect to the fast matching and the search space.
Yes. So we actually apply a variant of avial trees.
Okay.
And they're, I mean, we don't necessarily need the randomness, but they help for the storing of the Hamiltonian paths, if you mean that.
Okay. So storing of the Hamiltonian paths will then be probabilistically how do I say it, compressed, or it is much more efficient with respect to the other things, the other techniques that you have tried? Just to clarify from my perspective.
I'm not sure if I understand the question. So we also used AVL trees, and I think they were a very natural data structure to use. And I mean, yeah, we didn't necessarily need randomness for that. AVL trees are a good tool in general. I think there you have guaranteed amortized runtimes independent of the input.
Okay. Okay. Thanks.
Are there any other questions? Well, if not, then we can close this panel discussion. So thank you once again to all the speakers.